Okay, so good morning again. So let's get started. We're going to finish up on Newton's first law of motion. Again, Newton described three laws of motion, and we're finishing up on the first one. Um, and we look at forces, and we talk about contact force, and we went over description of contact forces, and then force at a distance. We look at those. Um, so, essentially, what is force? We try to describe what is force, and we know that force is measured in Newton, and the definition of 1 Newton is the force that is required to move an object of mass 1 kilogram with an acceleration of 1 meter per second, or 1 meter per second squared. So the Newton is equal to the mass, so again, force is equal to mass times acceleration. That is Newton's second law, even though we haven't discussed it as yet. But because force is equal to mass times acceleration, and the unit of force is the Newton. The Newton is the same thing as mass, which is measured in kilograms, and acceleration, which is meter per second squared. So the Newton is equal to kilogram per meter per second, sorry, kilogram times meters per second squared. Okay, so this is not, sorry, this should be a multiplication sign right there. Okay, so let me just change that. So this this is actually a multiplication sign. So let me see if I can change it. Okay, because again, force is equal to mass times acceleration, and acceleration is this, meter per second square. But meter per second square is meter per second per second. So this should be a multiplication sign. Okay. All right. So I think we got that straight. All right. So again, force is a vector quantity. And when we say vector quantity, it has magnitude and direction. So force going to have a certain magnitude associated with it, and it's going to be in a specific direction. And it's important for you to be able to draw the free body diagrams to describe force acting on an object. Because you might have multiple forces acting on an object. And, you know, just to further go over the different types of forces, again, we have two broad categories of forces. We have contact forces, and we have force at a distance. So when we talk about applied force, an applied force is is a force by a person, or could be an object, um, uh, causing, push or pulling of an object. So it's a force by a person or an object, and it's either a push or a pull on an object or a person. Okay? So this is a basic definition of applied force. So it's a force that is applied to an object. Either you push or you pull. And then we have normal force. When we talk about normal force, it is a support force exerting upon an object that is in contact with another stable object. So if you have the on the tabletop, book on the tabletop, then the book is going to be pulled downwards on the tabletop by the force of gravity. And the force of gravity on the book is equal to the mass times the acceleration of gravity, because force is equal to mass times acceleration. So the force on the book on the tabletop is equal to the mass times acceleration. But the tabletop is pushing upwards on the book to prevent it from going through the tabletop. So, and if the book is not moving, then you know the book, it's resting on a stable surface, so the tabletop is pushing back on the book with the same force that the gravity is pulling downwards. So that's what we call the normal force, and we'll show free body diagrams outlining the normal force. So the force of gravity pulls the book downward, and the normal force pushes upwards on the book. So that's what we call a normal force. And then friction, force of friction, another contact force, is the force exerted by a surface as an object moves across it or makes an effort to move across the surface. So it's very important for you to understand these different type of forces, because um, they're going to affect the overall motion of an object, and you have to know the proper definition of these forces. So a frictional force is one exerted by a surface on an object as it moves across uh, the surface or makes an effort to move across it. And there are two types of frictional force. There are two types of frictional force. One we call a sliding, and the other one is a static. You're going to get frictional force because when you have objects in contact with each other, there is an interaction between the molecules of those two surfaces, and there's a tendency for them to adhere to each other, to stick to each other. Okay? So it's going to take an effort to move one surface across the other surface. And you know, just imagine you have, say, a huge object. Let's take, for example, a refrigerator. You're trying to push it on the floor. It's going to take a little effort for you to move that refrigerator across the floor. Uh, you're going to expend a tremendous amount of effort initially. But once you get that refrigerator moving, it's easier to move. So you must have had these experiences. It takes a larger effort to start the motion. But once the object starts in motion, it's easier to move. So static friction is a larger number than sliding friction, because it takes a more effort to budge. Once you get it moving, it's easier to move. Again, there are two types of frictional forces: sliding frictional force. So once the object is moving across a surface, then the adhering of the two surfaces, the prevention. Again, remember that friction is going to prevent motion. So sliding frictional force is once the object is moving across a surface, and then static frictional force is before you get motion. Okay? Again, friction opposes the motion of an object. Okay? And the definition for friction is coefficient of so the frictional force between two surfaces is equal to mu. So this is actually mu times the normal force. Mu is what we call the coefficient of friction. Okay, the coefficient of friction. So mu is something like that. So frictional force is equal to mu times the normal force. And you have to remember this, because if you're gonna calculate anything which involve frictional force, you have to know that frictional force is equal to mu times the normal force, where mu is the coefficient of friction, and that's gonna vary it's gonna vary from surfaces to surfaces. So the coefficient of friction for say a book on a tabletop is different. It's going to different for different books on a tabletop. It's not going to be the same because again, different books going to have different weight. They're going to be made of different materials. So the interaction between those two surfaces is going to be different. So the coefficient of friction between surfaces is going to be different. Okay, but it's always the frictional force is equal to mu times the normal force. Okay, and again, that's a very important equation. So looking at frictional forces again, sliding frictional force, sliding frictional force is equal to mu, this is mu, times the normal force. Again, remember the normal force is the force pushing up on the object to keep it stable. Okay? Where this mu in the sliding frictional force is equal to the coefficient of sliding friction. So the coefficient of sliding friction is different from the coefficient of static friction. As we explain that once you get the surfaces moving across each other, it's easier to move it. Okay? So the coefficient of sliding frictional force is different from the coefficient of static frictional force. And the coefficient of static frictional force is usually, not always, higher than the coefficient of sliding frictional force. Okay? Because again, it's easier, once you get the object moving, it's easier to move it. Okay? All right. So again, air resistance. Say for instance, you jump out of an airplane or you're pushed out of an airplane. Um, the force that gonna push up on you is air resistance. So air resistance acts on objects as they travel through here. It opposes the motion of an object. So you're pushed out of the airplane and you're uh, coming downwards because the force of gravity is pulling you downwards. Air resistance is gonna push you upward. Okay, and later on we'll describe something called drag. What is drag? Um, so so again, air resistance opposes the motion of an object. Uh, it's most noticeable for objects traveling at high speed or with a large surface area. So drag is that force that is going to push upward on the object that's uh, 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 traveling or falling towards hurt. Drag is the force that is going to oppose that motion of the object falling towards earth. But drag is going to be affected by the speed of the object and the surface area. Okay, so those are the things that's going to affect drag or air resistance. Okay, and then tension, the force of tension. Force of tension is transmitted through a string. So if you're pulling on a string, two individual or multiple individual pulling on the string, the force that's generated in that string is called the tensional force. And then when you talk about a spring now, so you can have spring force is the force exerted by a compression or stretching of a spring. So I remember with a spring, you can either stretch it, pull it, or you can compress it. And if you pull it, if you pull a spring, the spring is going to try and pull back to its equilibrium position. So if you pull a spring, there's a force that's going to be generated to pull it back to its equilibrium position. And if you compress a spring, there's a force that's going to be generated to push it back to its equilibrium position. And we will discuss spring force later on. And then we come now to the gravitational force. So these now is force action at a distance force. So the ones that we just described is contact forces. And then now we come to action at a distance force. So there's no contact between the objects, but there's a force still being applied. And when we talk about gravitational force, you know, the different bodies in the universe or in the galaxy are going to pull on each other. The sun, which is at the center of our universe, is pulling on the planets around it, is pulling on the planets around it. And similarly, uh, us on Earth, once you're close to the surface of the Earth, you're going to be pulled in to the center of the Earth. Okay? So we describe that the force of gravity, so any force is equal to mass times acceleration. So the force of gravity is equal to the mass of the object times the acceleration of gravity. And we say the acceleration of gravity is 9.8 meters per second squared. So once you know the mass of an object and you multiply it by the force of gravity, sorry, the acceleration of gravity, then you get the force of gravity. Force is always equal to mass times acceleration. So um, we look at net force, and you know, Newton's first law. Again, Newton's first law states that an object at rest will remain at rest, and an object in motion will continue in motion in the same at the same speed and in the same direction unless it is acted upon by an unbalanced force. So when we say when the forces are balanced, you know, the book on the tabletop is a classic example. If it's not in, say it's not in motion, then the downward pull on that book is the force of gravity, and the upward push on that book is the normal force, and it's not moving. So all the forces acting on that book is balance. So balanced forces uh, do not cause an object to accelerate. You can get motion, you know, you can get motion with balanced forces. That is all the forces being balanced. Because if the motion is in constant is one with constant velocity, if the velocity is constant, you don't need a force to cause that motion. Okay? So it's important to know that for you to get an acceleration, for you to get an acceleration, you need to have a net force. You need to have an unbalanced force. And we're going to look at this in a little bit more detail. So to get the net force on an object, you have to do your vector sum of all the forces acting on that object. Again, unbalanced force is going to cause an acceleration. Unbalanced force is going to cause an acceleration. And it's important to note that the, the direction of the force will always be the same direction of the acceleration. The direction of the net force will always be in the same direction as the acceleration. So when we look at the free body diagram, if we look at this free body diagram right here, so we have an object say on a surface. The force of gravity, which we call the weight, is pulling downward on this object. And the force of gravity is the mass of the object times the acceleration due to gravity is pulling downward on this object. Normal force, which is the same magnitude as the weight, is going to be pushing upwards. So once it's on a stable surface and the surface is not moving, it's going to push upward on the object. Same magnitude but different direction as the weight. So the normal force is always in the opposite direction to the weight. And then if you apply a force, applied force, if the applied force is to the right, the frictional force is going to be in the opposite direction to the motion. Okay? So the frictional force is going to oppose the motion. And just before the object moves, you have your static frictional force. And then once it starts sliding, you'll have the sliding frictional force. But these are the force that will act on a stable object. Okay? And this is what we call the free body diagram. This is what you need to do. If you're describing any motion, you have to indicate the forces acting on the object and get the net force. The first thing you have to do is to draw your free body diagram, indicate the forces acting on the object, and then determine using your vector principle to look at the net force or to identify the net forces. All right. So if forces are balanced, so if all the forces are balanced, then you're not going to get any acceleration. Okay? Balanced forces do not cause acceleration. The acceleration will be 0 meters per second squared. If you have no acceleration, okay, then what it's telling you is that there are two things. If you don't have any acceleration, it's either the object is at rest. That means the velocity is 0. If there's no acceleration, it could mean two things. The object is at rest, hence the velocity is 0. Or the velocity is not 0 and the object is moving with a constant speed. Remember, the definition for acceleration is a change in velocity. You have to have change in velocity for you to get acceleration. If the velocity or the speed is constant, you won't have any acceleration. So 0 acceleration could mean the object is at rest or it's in motion with a constant speed in the same direction. All right? So if the object is at rest and there is no net force, it will stay at rest. If the object is in motion and there is no acceleration, if the speed is constant, it will stay at the same speed and in the same direction. This is Newton's first law, and you have to fully understand or comprehend it. All right, now we move on to Newton's second law. We've cheated a little bit, and we have talked about Newton's second law, even though we didn't fully describe it. But Newton's second law of motion states that uh, you need a net force to cause an acceleration. A net force is needed to cause an acceleration. So it described the behavior of objects for which all the existing forces are not balanced. So we look at Newton's first law. With Newton's first law, all the forces were balanced, and we showed you the forces were balanced. With Newton's second law, we look at the motion of objects in which the forces are not balanced. So you have an unbalanced force now. So an unbalanced force will cause an acceleration. Okay? An unbalanced force, or the same thing as if you have a net force. So if the forces does not all add up, then that's when you get a net force or an unbalanced force. And that is what will cause an acceleration. Okay? So what he stated was the acceleration of an object is going to depend on the net force acting on the object and the mass of the object. The acceleration of an object is going to depend on the net force or the unbalanced force and the mass of an object. So the acceleration of an object depends directly on the net force acting on the object. And the acceleration is going to be in the same direction as the net force. That is very important. You need to always have that at the back of your mind. The net force, the acceleration is going to be in the same direction as the net force. And that one statement is going to be very important for you, once you're doing physics problem. So always put that at the back of your mind. The net force or the acceleration is going to be in the same direction as the net force. So what he states is that the acceleration of an object depends directly on the net force acting on the object and indirectly on the mass of the object. So writing Newton's second law of motion, force, which is net force. So even though we put force, it's the net force or the unbalanced force. So when you do your algebraic summation of the forces, the net force, so it's not just force, it is the net force equals to the mass of the object times the acceleration of the object. Okay? So the acceleration of an object depends directly on the net force and indirectly on the mass of the object. So the greater the net force, the greater the acceleration. The greater the mass, the less the acceleration. So if you're solving for acceleration alone, then you get net force divided by mass. So you can see that the acceleration depends directly on the net force and indirectly on the mass. So the less the mass, the greater the acceleration. The greater the net force, the greater the acceleration. So let's derive Newton's second law. So what Newton actually said, is so we're going to derive Newton's second law. What Newton actually said was the net force on an object is equal to the change of momentum with change of time. That's actually what he said. But when you look at the change of momentum with change of time, it actually equals to the mass of the object times the acceleration that the object achieved. So let's look at the classic definition. The net force is equal to the change of momentum with change of time. Now we're going to cheat a little bit, and momentum is equal to mass times velocity. Momentum is equal to mass times velocity. So the net force on an object is equal to the change of momentum of that object with time. So the change in momentum is the mass times the velocity at some point in time, and you're going to subtract the mass and the velocity at the initial at earlier point in time, and you're going change in time is the time at some distant uh, time minus the initial time. So it's just a change in time from the initial time to the uh, later time. So again, momentum is mass times velocity. That is the definition for momentum. Mass times velocity. So change in momentum is on top and change in time is down the bottom. So that is equal to the net force. But if say for instance you kick a ball, if you kick a ball in the air, the mass of the ball remains the same. The mass of the ball remains the same. So at the earlier time, the mass of the ball is going to be x. At a later time, the mass of the ball is still going to be x. So the mass of the ball or the mass of the object is constant. So what you have is a change in velocity up top, okay? Change in velocity up top and change in time at the bottom. Remember the definition for acceleration? Acceleration is a change in velocity, okay? Acceleration is a change in velocity, okay? So that is why in our final analysis, we have that the net force is equal to the mass times the acceleration, because this quantity here is is acceleration. Okay, remember the unit of velocity is meters per second, and then below you're going to have time, which is in second. So you're going to have meters per second square. Meter per second square is acceleration. Or change in velocity is equal to acceleration. So that is why the final analysis, we have the net force is equal to mass times acceleration, using the fact that a net force is equal to the change in momentum with change of time. Okay? All right, and we use this aircraft to show that at the at an earlier time, this going to have a certain momentum. At a later time, it's going to have uh, another or a different momentum. The mass of the airplane is going to be roughly the same. The velocity, however, is going to be different, and the time is going to be different. But so when you take out the mass, you have a change in velocity with respect to time. Change in velocity with respect to time is acceleration. So Newton's second law states that net force is equal to mass times acceleration. So the acceleration of an object as produced by a net force is directly proportional to the magnitude of the net force and in the same direction and inversely proportional to the mass. We'll show that before. But the important takeaway message here is that the acceleration is going to be in the same direction as the net force. Acceleration is going to be in the same direction as the net force. The greater the magnitude of the net force, if you look right here, and so again, acceleration is equal to the net force divided by the mass. So the greater the net force, the greater the acceleration. The greater the mass, the less the acceleration. So the acceleration is directly proportional to the net force and inversely proportional to the mass. Very important. And so if you push this object with a certain amount of force, it's gonna, have a certain speed acceleration. If you use a larger force, you're going to get more acceleration. The speed is going to increase faster. Okay? So the greater the net force, the greater the acceleration. So when you're doing analysis using Newton's second law of motion, there are some things that there are certain forces that you need to comprehend and understand. When we're doing analysis of motion using Newton's second law, you need to know the net force. Net force is usually equal to, because once you have a net force, you're going to have acceleration. We just showed you that. So net force is equal to acceleration of the object times the mass of the object. Okay? You need to also know that 1 Newton of force is the same thing as 1 kilogram. This is times again, times, so remember, force is equal to mass times acceleration. So let's change this. So this is 1 Newton of force is equal to 1 kilogram times the acceleration, which is meters per second squared. Okay? And you also need to know that the gravitational force is equal to the acceleration times the mass. But when we talk about gravitational force, the acceleration is actually acceleration of gravity. And it's represented by little g. Acceleration of gravity represented by little g. The acceleration of gravity close to the Earth's surface is 9.8 meters per second squared. And that's another number you have to remember. Okay, the acceleration of gravity close to the Earth's surface is 9.8 meters per second squared. And when you're talking about frictional force, it's equal to mu, coefficient of friction, times the normal force. So frictional force is equal to mu times the normal force, where mu is the coefficient of friction. All right. So the gravitational field strength, so that's the force. So that is the force. If you're close to, well, if you know, if you're in the vicinity of Earth, then you're going to be pulled, the force that you're going to be pulled with is equal to the acceleration times the mass, but the acceleration is the acceleration of gravity. So if you were to solve for that acceleration due to gravity, is equal to the gravitational force divided by the mass. We know gravity force is in newtons and mass is in kilogram. So the gravitational force is equal to Newton per kilogram. So what this is saying is that meters per second squared, because remember this is acceleration due to gravity, which is meter per second squared. The meter per second squared is the same thing as Newton divided by kilograms. All right. Again, a net force is going to cause acceleration. Net force causes acceleration, and the acceleration is going to be in the same direction as the net force. So if the direction of the acceleration is known, then the direction of the net force is also known, and vice versa. Very important to just these two statements is critical for you to fully analyze the motion of objects. All right, so let's do a little exercise in looking at net forces, because before you can do any analysis of motion, you have to look at your free body diagram and calculate your net force. So look at in situation A, this is a free body diagram. Gravitational force is pulling on this object, 3 newtons. Remember, the normal force is going to be in the opposite direction and the same as the gravitational force. So the normal force is in the opposite direction, still 3 newtons. You have an applied force to the right, 5 newton. Frictional force is going to be in the opposite direction to the motion, and it's 5 newton. So all these forces are balanced. So this is this is balance force. So Newton's first law spoke about this, you know. So is either this object is at rest or it's in motion with a constant velocity and in the same direction, okay? Direction not changing. And but if you look at this scenario, it's different. These forces are not balanced. Gravitational force of 3, normal force is in the opposite direction 3, but the force acting on this object is just a frictional force to the left. Okay, this is a scenario where this object is actually slowing down. So if this object was in motion to the right, but it's slowing down because the frictional force is slowing it down. So the net force uh, is a force. So there's actually a force to the right, but the frictional force is overcoming that force. And the net force is actually 5 newtons to the left because this object is slowing down. It was moving to the right, but it's slowing down, and the net force is 5. So the net force here is 5, slowing this object down. So there's an acceleration. Remember, the acceleration is usually in the same direction as the net force. So there's an acceleration on this object, but the acceleration is to the left. Therefore, if the object is moving to the right and the acceleration is to the left, that means the object is slowing down. It's decelerating. We'll get back to that. But anyway, another scenario, situation C, where free body diagram, the gravitational force, which is equal to the mass of the object times acceleration due to gravity, 20, and the normal force is in the opposite direction, and the same thing as the gravitational force, and it's 20. So this is an object uh, uh, with, with no unbalanced force. These forces are balanced. So, okay, so it could mean that this object is at rest or it's in motion with constant velocity. But this situation, if you have an object which is say falling to earth and there's an air force which is pushing up on the object, okay, so in essence it start moving upwards now. Okay, you do your same thing. Gravitational force is equal to the mass of the object times the acceleration of gravity, but the air force which you calculate whichever how is for 40 newtons. The net force is upwards. So this object is going to move upwards. Remember, the net force is going to be in the same direction as the acceleration. So there's a net force uh, which is going to push this object upwards. It's going to overcome the force of gravity because it's more. And when we do free body diagrams, the arrowhead indicate the direction, and then the length of the arrow indicate the magnitude of the force. So you can see that the length of this arrow is greater than this one, indicating that it is of a greater magnitude, and then the arrowhead indicates the direction. So these are free body diagrams. So look at let's continue our exercise. So if you get a free body diagram like this, okay, force of gravity 200, and if it's on a stable surface, then you know that B, which is your normal force, is going to be the same as your force of gravity. Okay, this is telling you your net force is 0. The net force is 0. So these are balanced forces. So therefore, force of gravity, 200, we know that the normal force, which is opposite to your force of gravity, this is going to be 200 newtons. And because your net force is 0, then if this is an applied force, then the force of friction is also going to be 50 to the left because your net force is 0. Okay? In this scenario, they say that the net force is 900 up. Force of gravity is 200. So therefore, your upward force have to be uh, 200 more than this 900. So it has to be 1100 up because the net force is 900. So this upward force is 1100 newtons because when you subtract 200 newtons from your 1100 newtons, you get 900. So the net upward force is 900 newtons. So your net force is 900. In this scenario, the net force is 60 newtons to the left. 60 newtons to the left, net force. So you have to indicate all the forces acting on this object. So again, your normal force is 300. Okay? So therefore, if this object is on a stable surface, then your force of gravity is going to be 300, similar to your normal force. Okay? So these two forces balance each other out. But there's a net force to the left of 60. So your force to the right have to be 20, because 20 from 80 give you 60 to the left. So these are not balanced forces. So the force to the right is 20. The net force is to the left and it's 60. So therefore your acceleration is going to be to the left. Acceleration is going to be in the same direction as the net force. And then when you look at this scenario, okay, there's the net force is 30 newtons to the right. This is the force of gravity if it's on a stable surface. Force of gravity H. Normal force is F. Again, your normal force is going to be the same as your gravitational force, force of gravity, if it's on a stable surface. There is a force to the right, a net force to the right of 30. That is when you subtract the force to the left from the force to the right. So your force to the force to the right have to be 50. So this force G, the force G is 50 newtons, but the net force, when you subtract 20 from 50, you get 30. So that's 30 newtons to the right. That is the net force. Okay? Net force will give rise to acceleration. Net force cause acceleration. And the acceleration is going to be in the same direction as the net force. So let's do a quick exercise because you have to understand and know how to use these information in equation. So let's look at this case. So if 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 you are to determine the acceleration that result when a 12 Newton net force is applied to a 3 kilogram object and then a 6 kilogram object. So let's see what this is. So it said determine the acceleration. So we know that acceleration is equal to the net force divided by the mass. Net force divided by mass. We know that. So the question asks, determine the acceleration on a 12 Newton net force. So the force is 12 Newton of net force is applied to a 3 kilogram object. So it is 3 kilogram. So 12 divided by 3 is 4. So that acceleration is 4 meters per second squared. And then to a 6 kilogram. So it's applied, the net force was applied to a smaller object and then a larger object. So for the larger object, it's the same force, 12, but the object is larger in terms of mass. So the acceleration here is 2 meters per second squared. So again, the larger the force, the larger the acceleration. The greater the mass, the less the acceleration. So in this scenario, we had a larger mass, and you can see that the acceleration was less. And that is because your acceleration is directly proportional to the net force and inversely proportional to the mass. So the greater the mass, the less the acceleration. Okay? All right. So let's look at another scenario. So in the second scenario, a net force of 50 Newton is exerted on an encyclopedia to cause it to accelerate at 5 meters per second squared. Determine the mass of the encyclopedia. So using the equation again, all right? So again, if you want to start from, force, net force, that is, net force. So let's get this this F a little bit better. So force is equal to mass times acceleration. Okay. So in this situation, they want you to determine the mass. So the mass is equal to force divided by acceleration. So the mass is equal to the force divided by the acceleration. So the net force is 15 exerted on the encyclopedia and cause it to accelerate at 5 meters per second squared. So the net force is 15, and you're going to divide that by the acceleration to get the mass. So 15 divided by 5, and that's equal to 3. So the mass of the encyclopedia is 3 kilograms. Okay? So you have to use net force. So, and the acceleration is going to be in the same direction as the net force. So just using the equation, net force is equal to mass times acceleration. To get mass, you divide the net force by the acceleration and you get the mass. Okay? All right, so I think we're clear with that. And then we have another scenario. All right. Okay, so this scenario is, suppose that a sled is accelerating at a rate of 2 meters per second squared. This is the acceleration. If the net force is tripled and the mass is doubled, then what is the new acceleration of the sled? So, you always start with what you know. You know that. So we know that the force from Newton's second law, force is equal to mass times acceleration. Okay, so force is equal to mass times acceleration. So they said that the sled is accelerating at a rate of 2 uh, meters per second squared. So the acceleration is so let's change this around and put acceleration is equal to the force divided by the mass. Okay, so acceleration is equal to force divided by the mass. So what they say, if the net force is tripled, so if you triple the net force, so you're going to increase it by 3. So whatever the force was, you're going to now get 3F, okay? And then, so call it 3F. All right, so you triple the force. So whatever it was, you multiply by 3. And then the mass is halved. So the mass now is half. So it's a half times whatever the mass was. So again, if you triple the force, the net force that is, you're gonna increase the acceleration by 3 times. But if you halve the mass, you're gonna increase the acceleration again by 2 times. So when you solve this, you'll get 3 times, because you're dividing by a half, so it's 3 times 2, okay, and you still have your force and your mass, whatever the net force and the mass was. So then what is the new acceleration of the sled? The new acceleration of the sled is gonna be 6. It's gonna be 6 meters per second squared. Okay, because your initial acceleration was 2, which is force divided by the mass, whatever it is, but you increase the force by 3, you halve the mass. So what you're actually doing, you're changing everything by 6 times. Okay? Sorry, 6 times. So what is your new acceleration? What is the new acceleration of the sled? So it is 6 times 2, which is 12. You're going to increase it by 6 times. Okay? You're going to increase the new acceleration 6 times. But the initial acceleration was 2. So it's 6 times 2, which is 12. Your new acceleration of the sled is 12 meters per second squared. Okay? So just think about this. I mean, they didn't give you the net force and they didn't give you the mass, but the net force increased 3 times. The mass decreased by a half. Okay? We know that the net force divided by the mass is 2 from the initial statement. You're going to get an increase of 6 times. 3 divided by a half is 6. The net force divided by the mass is 2. So 6 times 2 is 12. Your new acceleration is 12 meters per second squared. So you know, you just have to understand what you're asked and then use the information to solve your equation. Let's see something. So right, so let's we're gonna stop here and then when we